fishing line. All you really need is patience. Alright, okay, obviously clickbaity title. You knew that coming in. Don't pretend you didn't. So what are we talking about? We're talking about my CNC machine. This is a Core XY design, as basic as I could make it. CNC plasma cutter. We've attached our plasma cutter to it. And the fishing line is the stuff that's doing all of the actual drive. So it's sort of a little bit etch-a-sketchy. When the power is off, you can just sort of manually move things around. So if you're not familiar with Core XY, there's this complicated thing where there's basically two motors working in unison, and they each are in the middle of a loop. So basically one side, well, I guess this side, connects to the carriage, around a post, around the motor, around a back post, around this post, to that side, and an inverted mirror of that thing. And normally you do that with timing belt, so that you can make sure that you translate rotation of the motor into precise linear motion. I'm doing it with these 3D printed, what I'm calling capstans. There's basically 4 or 5 coils of the fishing line around the motor, around the capstan, that creates enough friction that it shouldn't shift whilst moving. So when the motors rotate, you get a precise amount of linear motion. And that is the fundamental basic of this machine. Let me bring you in a little bit closer so you can see some of the more details. I'm going to talk about what I did in designing this machine. We'll do some quick cutting with it, and then we'll talk about why I'm building a different one. So this is the capstan design. This hole here is a grub screw onto the motor, and what you can see is there's basically a thread to it, to create this situation where each one of these turns doesn't sort of overlap with each other. And what that means is that you have this incoming line at the bottom and this outgoing line at the top, and on the other side it's an inverted thread, so the inline coming on the bottom on this side and out on the top. So one of the things that you get when you do a Core XY with belts is that you have one motor is on essentially at the high side and one is on the low side, so that when the belts cross each other, they don't clash. This is slightly different because each side pulls in on the low end of the capstan and leaves at the high end of the capstan, and all that means is that my lines cross at the back here, but because it's just fishing line, that's not a big deal, and it means that I have all of the lines are flat and parallel, joining into the main X carriage. Oh, I should probably mention that the specific fishing line is Kevlar braided and rated for like £100 or something, whatever that is in real terms. Basically, it's strong, it can take a lot of tension, it doesn't stretch, which are all things which are very useful in this design as well. So that's the basic structure. One of the great features of Core XY, which I guess makes it very popular in 3D printers, is you have quite small motors, but because both motors have to essentially coordinate for almost all motion, unless you're going directly diagonal, like if you go directly diagonal, you're only using one motor to do it. Every other motion you have both motors in coordination, and that means you sort of get the power of both motors behind every move. Which again is quite a good feature in this lightweight thing where you're using very small motors. So briefly, let's talk about the rail design here. This whole build is really a feature of whatever random scrap I have. So I had a bunch of steel rod that I had bought, which the rest of it is still down there, that I had from a previous project. So I decided to use 3 lengths of it and just 3D print these brackety things. There's one down here. So this just clips and holds that spacing. And then this carriage, let me see if I've got one that's a bit easier to see. So then this carriage is basically one of these. So there's one on each side and there's one under here, and that is just this profile, and I basically embedded these 4mm ball bearings in, and that means that you can kind of just clip them in place, and then they somewhat low friction, not perfect, but somewhat low friction, run in a linear fashion. So this was basically the cheapest, most basic thing I could think to do to create sort of a nice linear path. And then I say they have threaded holes through the top, so you can mount different brackets and whatnot. And as I've evolved this idea, I've sort of added different bits. So obviously on these sides, there's this effectively L bracket that holds the bearings and sets the holes for the 3 rods that run cross rail. At some point I decided there was a little bit, in an attempt to defeat the fundamental flaw of this design, which we'll come to a bunch, I ended up creating another bracket to run this top rail that holds sort of retaining bracket, so you end up kind of squidged between these two things, which was a hope to try and prevent it from pinging itself out and leading too much. It's somewhat effective, because, spoiler alert, this is not the most rugged or stiff of setups. If I do this, you will see how much motion there is. But the goal of this, I mean, originally I built this kind of to test with like a pen platter, very lightweight. This torch is obviously pretty beefy and heavy. I've got it kind of supported up here. And I've gone through about 3 or 4 different designs for the Z-axis. In version 1, I just had a servo. It was like lifting a pen on a rack and pinion, which was sort of okay, but a bit underpowered, and the servo was not super reliable at positioning. Then I went up to a small stepper motor, even smaller than these. And yeah, we've done through a bunch of different designs. This is where we're at right now. So let's look at the Z-axis design. So at this point, I would say the Z-axis is a fairly classic design. You kind of have a back plate, a top plate, a foot plate, a threaded rod that sits in a bearing at the bottom of the foot plate, runs through the carriage block into a coupler for the motor. So spin the motor, twist the threaded rod, and up and down you go. And this threaded rod is literally just one of these where I trimmed off the top. I originally actually drilled a countersunk hole in through the shaft to take directly onto the shaft of the motor. That was a bad idea. It turns out there's a reason that you get these slightly flex couplers that can survive a little bit of misalignment. So 3D printed a flex coupler, and yeah, basically just threw screw threads through this block. And then what we have on the front here is the latest edition, which is a floating head. So we have these V-rule bearings, and you can see this block in the middle, which hopefully resists lateral, resists it wanting to do this, but lets you, if you hit the surface, come up. And you'll see here we have a sensor. So the theory of this whole redesign was that you would be able to touch down onto the steel. It would push this up. You'd find your Z offset, and you would be able to continuously just recheck where you are for 0. That was the theory. But the aforementioned flexi, because of how far the torch is, actually when you drive Z down, the first thing that happens is the whole carriage wants to twist, which locks this whole thing up. So this does not work in this current arrangement, which is why I'm going to build a different CNC machine. But this one is going to go back to being a pen plotter. It's pretty good. We'll use it right now to do some stuff. And what we're going to use it for, hopefully, is to cut some parts for the new design. If you've watched any video about DIY plasma cutting, something that probably came up, or maybe was just a given, is that you should not use high frequency start plasma cutters. Either that, or you saw someone struggle a lot wrapping things in aluminium and trying to deal with the interference. Because a high frequency start is what you get in cheap, relatively cheap plasma cutters. It makes it really easy for manual start. You don't have to do anything clever. It just spikes a high frequency arc to create the initial arc and off you go. That's fine, but it has the effect of, well, in my case, it reboots the monitor that I'm using to control the CNC machine every single time. And it will really mess up your electronics very quickly. So part of the reason of going Core XY, one of the reasons of going Core XY, was to keep all of the motors at one end of the machine as much as possible. I wanted to try and avoid having cables routing in odd ways. I have the whole electronic body sat in this empty old PC case in the hopes that that was going to help with the EM situation, but it's basically just a 24-volt power supply with, I think you see in there, an ESP32 wired out to some outputs that drive the two big drivers and one small one for the Z-axis. This, again, was largely, I already had ESP32s, I already had the power supply, I already had the small stepper drivers, and I did end up buying the slightly bigger ones. Let me switch it on. So one of the biggest challenges of using a cheap hobby plasma cutter to run a CNC table is that you're basically fighting this massive EM spike that is going to mess with you. I have run into that a bunch. I've gotten an alignment, an arrangement of cables that seems to be working, and it basically amounts to keeping the plasma torch cable and the earth torch cable as far separated and running in a different spatial orientation to the motor cables. And just like that, basically works. So with the machine there and the ESP32 there connected over Wi-Fi, I have the shop machine here suspended from the ceiling running a generic G-code sender that happens to support Fluid NC, which is basically a Grebel clone. But this has a Gerbil clone. And this has a number of slightly nicer features, like a preview of the job you're going to run and where the tool is, all that kind of stuff. So we can use this to control it, and we can use it to run commands. So if I point you down there, and I hit, for instance, Z up, you can see us doing Z moves up and down, and we can go and control ourselves to position. And then when we're in position, we can just zero off our location, which then shows us that the tool is here relative to the cuts we're going to make. And so we've set our machine. We've told it that this is our XY0. And I'm just going to load up my part, which looks like this. And then we're going to let her rip. Ta-da! There we go. So we have cut out a part. Now you will have noticed there were 4 short hits at the end. That was intentional. Trying to do a 5mm, like trying to do a small hole on this thing is impossible. So that's just spotting the locations that I need to drill. And effectively this is a bracket that is 2 screw holes to mount and 2 holes for the bearing axles to hang off the back of a future XY. Now, the astute among you will have noticed that there are a bunch of failed attempts at cutting on this, and you may have guessed that this didn't go as easily as maybe the edit makes it seem. So let's talk about what's not good about this design. So I'm going to say it is theoretically workable. This particular piece I had to do a bunch of grinding just to get it released, because I think despite my efforts I did end up going way too slow. And the reason I went too slow is I spent a lot of time off camera fighting with motor stalling and having to bump the power up and faff around and basically fight a fundamental flaw of the machine, which I mentioned earlier, which is that these rails are not great linear rails. The carriages ride on top of them, and the ease with which they pop in is also the ease with which they pop out again. There's just not, they're not clamped well in place. They will move, but there's much more friction than there would be for a proper linear rail. And when you're then adding the weight of a torch, like particularly the weight of the torch ends up having to be so far off the carriage, you're just applying a lot of extra forces, and all of those inaccuracies in this very janky setup build up. So I have successfully used it to make this. I cut brackets, I cut this random plate with a piece of text in based on the Pepsi Max logo. Not sponsored, I just drink a lot of it. So yeah, basically I've got bits and bobs of failed but plausible looking plasma cuts. I even made is this. So this design has these NEMA 17 motors on these metal brackets that came with the motors. So I made my own. So I don't know if it's super clear. Obviously I painted it. This was cut as a flat pattern. The holes were spotted originally, well, the small holes were spotted, and then I drilled them. Now, is this perfect? Absolutely not. Absolutely not. And this is kind of, I think, probably the best representation of the potential of a machine like this. It is not, at this sort of incredibly cheap price point, a perfect ability to cut things out. But what it is a very fast metal saw, right? Like you can kind of cut a fairly complicated pattern, get it close enough. If you allow tolerances, you can then stick it in a mill, clean up the edges, drill the holes, etc. So this was probably the first piece that I made that made me think that it was functionally useful, and as I have played more with it, I have come to the conclusion that I would like to make a slightly better version of this, to really hone in on the potential. We made this kitten-themed bottle opener, which then I put a handle on. It's a little bit janky, but hopefully you can see the intention of the design. So, all of this to say, having a CNC machine for your plasma is cool, it's workable, but the super low janky setup that I came up with is just a little too unreliable for this. I've destroyed a lot of steel with silly problems. So, in keeping with the basic idea, which is that I hoard materials and stuff, and I'm going to try and make machine out of what I have on hand, I have a plan B. Those who have watched my channel before, or a bunch of previous videos, may be familiar with the fact that I do in fact own a somewhat proper CNC machine. This is a big CNC router. This is like the third iteration, I think, of me trying to build a CNC router. The middle iteration was just buying a CNC machine from the folks at Usenest. I bought the Usenest Ox many years ago now, and that machine was all this like 60-20, 80-20, 20-40, whatever profile, aluminium extrusion profile. And when I took that machine to pieces to build this, my custom version, I refactored a lot of that extrusion into the structure of this, as well as adding metal frame and whatnot. But I have this 60-20 and another length of, I think, 40-20 that are 1 meter long that I just still have. And the machine that I was building, the basic plasma table, is about 1/2 meter by 1/2 meter. It's actually a little bit smaller than that. But I have enough of this extrusion to make a solid frame. I also, many years ago, had the idea of doing like a camera slider thing. So I have this pretty thin, small linear rail, but I only had one of them. So I have now purchased a second one that is identical, which does mean I bought something, but it is to reuse a thing that I have. So my new plan is to cut the 60-20 in half, bolt one of these to each side to have a 1/2 meter run, and then whilst I bought this for a single camera slider thing, I don't remember, it was a long time ago now, I ended up buying another much beefier bit of linear rail, some HG15, whatever it is. It's very similar to the stuff that is on the Z-axis of this. This is actually slightly beefier. So I also have a 1/2 meter of this of a beefier rail, and that is going to be the X gantry, X-axis. So yeah, long and the short of it, I'm going to do another one of these machines using somewhat improved parts, but still mostly delving into the scrap pile of the stuff that I have accumulated over the years. So it's difficult to estimate what something like this really cost. I do, obviously, I've not talked about this yet, I have this metal frame with essentially standard plasma table slats in it, which I whipped up quickly. The slats were, I think, 30 quid for a set of 10, and they obviously are replaceable. The steel I already had on hand. I bought a big plastic storage container that is sitting underneath it with water in it, which makes a big difference to trying to avoid so much particulate getting into the air. Like if you can, if you're cutting and most of the sparks are going all the way through and straight into water, it like really improves the air quality. Obviously I have the door open anyway, I'm wearing a mask anyway, but like how quickly the room is fine again makes a big difference. So that's all kind of ancillary to the machine, but obviously does cost money to have. The machine itself, like if you were actually buying these components new, I did try to estimate. I think it's maybe 50 or 60 pounds worth of stuff in motors and drivers and ESP32s and like steel, etc. It's very difficult to figure that stuff out because obviously once you start factoring in delivery, blah blah, is obviously, to me this feels almost free because the vast majority of this stuff I just had. And this is where doing lots of projects over a long time and doing stuff like, in order to make up for a free delivery, adding to your metal order and adding to other orders, means I've sort of acquired a bunch of stuff like motors and motor controllers and aluminium extrusion and linear rails. So the next one won't be quite so basic, I hope. I'm going to go to timing belts. As much as fishing line has been a fun, interesting way to do this, there's probably a reason that everyone uses timing belt, and then that is kind of inexpensive. Yeah, as a proof of concept for taking fishing line and some basic parts and making a semi-functional plasma table, functional enough, dare I say, maybe not. It was a good taster, and it's got me inspired enough to build a proper one, or at least a version 2 significantly improved. I think with proper linear rails, like linear rails, just that's really tough to make something good. There are certain engineering tolerance type aspects that are quite difficult to DIY your way out of, even with a 3D printer and like a reliable linear rail. That's a tricky one. All right, I'm going to wrap it up here. Hopefully this was mildly interesting to some people. I will continue to do interesting things to improve this, and maybe, who knows, I'll get to the point that I can actually reliably cut fairly precise patterns. We shall see. Thanks for watching. See you next time.